Welcome to the third week. For this week, we'll discuss theoretical aspect of Geographic Information System, also known as GIS. Do you remember the integrated framework of 4 disciplines for spatial data science and applications? From the integrated framework, we'll discuss the first discipline, GIS. What is GIS? GIS generally stands for Geographic Information System. It can be defined as a combined framework of hardware, software, people, data, organization, and policy regarding spatial data and the problems. From functional perspectives, it can collect, store, manage, query, visualize spatial data, and output maps. From software perspectives, it is partially a CAD, computer-aided design for data production, a DBMS for data management and query, a data analysis tool for spatial data analysis, and a visualization tool for mapping and cartographic representation. GIS is composed of 5 layers from system perspectives. The very bottom layer is Spatial Reference Framework, which can make spatial data have locations on the surface of the Earth. The second layer is Spatial Data Model, which is about abstract representation of the real world. Third layer is Spatial Data Acquisition System, which is about how to fill the spatial data model or how to produce spatial data. The fourth layer is spatial data analysis, in which some useful information or insight can be extracted from the spatial data. The final layer is mapping and geovisualization of dissemination and delivery of spatial information. These 5 layers should be all combined. Then we can build some GIS applications, which can be also considered as applications of spatial data science. Now let's take a look at one layer by one layer. The first layer is Spatial Reference Framework. It is about coordinate system with origin and orientation. Think about it. The Earth is a 3D object, but map is generally 2D representation. The dimensional difference between 3D and 2D requires a series of transformations in which you have to understand concepts of physical Earth, geoid, ellipsoid, datum, and map projection. As long as you understand these concepts, you can interpret any coordinate system all over the world. There are 2 different views of the space: object view or field view, which is about how to recognize spatial reality. In the object view, the space is composed of discrete objects with boundaries, or path, or point location, and so on. In field view, space is filled with continuous phenomena, like elevation, precipitation rate, and so on. For object view, a vector model of point, line, polygon is suitable. For field view, a raster model is generally more appropriate. There are some specific variations of vector models and raster models. For representation of graph data structure, network model is used in GIS. TIN, which stands for Triangulated Irregular Network, is a vector model, but it can be used for a field view. DM, Data Elevation Model, is a raster data model for representing the shape of the terrain. For spatial big data, they are also based on either vector or raster format. More detail will be discussed in one of the next lectures. The third layer is Spatial Data Acquisition System, which is about how to produce spatial data. There are numerous ways of building and collecting spatial data and spatial big data. First of all, government's open data infrastructure should be the starting point of spatial data acquisition. Most of governments generally offer free access to spatial data, which are produced with tax money. Other examples are conventional surveying method, analog data conversion, GPS and other sensor data, and check-in, check-out. And human manual input is also used for basic spatial data production. For raster data, aerial photogrammetry and Earth observing satellite imaging systems are the method. And recently, radar and LiDAR system is intensively used for 3D spatial data production. Spatial data analysis include methods from basic spatial data processing to highly advanced data analytics, measurement of length and area, and geoprocessing such as intersection, union, and clipping. They are basic spatial processing. Conventional spatial data analysis would include proximity and accessibility analysis to a certain service, spatial autocorrelation and spatial interpolation, which are closely related to each other, spatial categorization, including classification, clustering, and hotspot analysis, and spatial factor analysis for finding inferential variables for a certain spatial phenomena, and terrain analysis about land surface processes. Recently, network analysis draws more and more attention due to graph structure of spatial big data. However, in reality, network analysis has a long history in spatial data analysis, such as shortest path algorithm. Spatial temporal data mining and trajectory analysis recently gained more and more importance due to their relationships with spatial big data. The last layer is mapping and geovisualization for information dissemination and delivery. As mentioned, it is one of the major strengths of GIS of other related disciplines. For that, you have to understand the concept of scale and map generalization, and map element and typography. There are different types of thematic mapping. Modifier aerial unit problem is an interesting and unique issue in geovisualization. While temporal dimension can be incorporated with spatial data, map animation is used as a very powerful means to deliver the spatial change over time. Also, web mapping service is an important issue, although it is not only geovisualization issue, but also an information system issue. But there are more and more web mapping systems for spatial information delivery. All in all, you have discussed the first layers of GIS, from spatial reference framework to mapping and geovisualization. In a series of next lectures on GIS, you will learn each layer in more detail. Stay tuned and see you in the next lecture.